Assalamu alaikum, students. Can you hear me?
Walaikum salam, sir.
Walaikum salam. Yes, sir.
So today we are going to start or continue from where we stopped last time. We started studying the chapter number 5, which is about the application of first law of thermodynamics over open systems. Chapter number 4 was about the application of first law of thermodynamics to closed systems. This chapter is about the application of first law of thermodynamics over the open systems. And we are going to study different devices for the open systems and how to apply the first law of thermodynamics over them. We started studying that last week, and we discussed about the formula for the mass flow rate, since now there will be flow going in and out of the devices. And we started studying two devices. We talked about two devices, which is the nozzle and the diffuser. So anyways, before moving forward, I need to ask, is there anything within the chapter anybody studied and found any difficulty in understanding any topic, anything? Please feel free to ask. I know you had assignments and you have quiz, so most probably students were focused over the first three chapters only. But still, if anybody has gone through the material in chapter number 5, which we covered, you're most welcome to ask. Okay, regarding the quiz and the assignment, anybody have anything to say? Anything which is to ask? Or
Sir, in the assignment, I think it was harder to do the question. No, it was hard to do question number 5 for me. It was
so
very complicated, I thought.
it was very complicated. In which sense it was complicated? You thought that parametric study was difficult, or writing the equations for that
Using
stuff?
the property plots to draw graphs
Well,
of PV graphs,
PV graphs, property plots was difficult. Okay. So did you attempt it? Did you try it?
I did, but I couldn't complete it properly.
Okay. But anyways, you submitted your assignment?
Yeah, I have. I've done the rest.
Okay, good. Good. Anyways, we're going to discuss about that later as well. Okay. So we're going to talk about the property plots, how to develop it, how to do it. So I'm going to take a survey from the students regarding what difficulties the students really faced in the assignments, and then we are going to have a session where we're going to discuss about those difficulties.
Okay.
Any other thing you feel difficulty? What about the quiz? Was the quiz really difficult?
No, it wasn't. I didn't think so.
Okay. Okay, anyways, so because since we have very limited time of our lecture, so right now I want to get focused over the lecture once again. We're going to discuss about these contemporary issues later when we have time. So let's discuss about the chapter number 5, which we were studying. Okay. So first of all, just to summarize what we did before was that we know that we have the first law of thermodynamics. The first law of thermodynamics states that Q minus W plus E mass in minus E mass out is equals to delta U plus delta kinetic energy plus delta potential energy. Okay. This is the first law of thermodynamics. When we are applying this first law of thermodynamics to chapter number 5, now here we have open systems, but what we do is that we say that this is SFSS, which is basically, yeah, FSSS, which is basically steady flow, steady state. When we say steady flow, steady state, what does it mean? It means that no change with time. When we're saying no change with time, means the initial condition would be the same as the final condition. When we say initial condition be the same as final condition, so all these three terms would be zero. So all these three terms would be zero. It's okay, no problem. So now what we have here, we have Q minus W plus E mass in minus E mass out. Now, for many of the devices, we have only single mass flow inlet and single mass flow exit. So E mass in minus E mass out will come out to be M dot change in enthalpy, because now we are talking about the fluid going in and out of our system. So when the fluid is going in and out of our system, so whenever the fluid is going in or fluid is going out, so there are different kind of energies associated with that fluid, and those energies are basically enthalpy. We have kinetic energy, we have the potential energy. So the difference in these energies would be the E mass in minus E mass out. So it will be M dot H1 minus H2 plus M dot V1 square minus V2 square upon 2 plus M dot G Z1 minus Z2. So if you add all these terms, since that is a steady state, steady flow devices, SFSS, so basically summation of all these things will be zero. So this is the first law of thermodynamics, and this is the equation of the first law of thermodynamics, which we are going to analyze, which we are going to apply in this chapter to different devices. Before moving forward, is this equation clear or not? Is there anything which is in this equation which is not clear? Please feel free to ask. Is this equation clear?
So all of this is going to be used?
Yes, all of these terms are going to be used.
Or will some of these turn to zero?
Yeah, they will turn, some of them will turn to zero. The next table that you see down is about when we apply this equation to different devices, which terms will be there, which will not be there. So we are going to discuss about that. Okay, so some of the terms will definitely go to zero, but we will see that which ones are going to go to zero and which ones not. Okay, but important thing is that, do you understand this equation or not? So this equation is Q minus W, and E mass in minus E mass out is basically this term whole. Okay, but if for the case when you have single mass inlet and single mass outlet. Okay, so now let's study the devices one by one. Remember, this is a summary sheet which I have made here, and this summary sheet is going to help you a lot in your preparation for this chapter, and this is kind of a big picture in front of you. So we're going to analyze things based upon this big picture, so that things would be easy for you to study when we go through the chapter slides itself. Okay, so here let's first discuss about the devices. The two devices which we discussed last time were nozzle and diffuser. Okay, now what are nozzle and diffuser? They are basically pipes. Both are pipes, but nozzle is a pipe with decreasing diameter. So the diameter is decreasing of the pipe. And diffuser is opposite to nozzle, and it is a pipe with increasing diameter. So here when we say 1 and 2, 1 means inlet, 2 means outlet. Okay, so 1 means fluid going into the system, 2 means fluid moving out of the system. Okay, so we have for the case of nozzle and for the case of diffuser. For the case of nozzle, the pipe is having a diameter decrease as it moves from inlet to outlet. For the case of diffuser, the pipe diameter is actually increasing. For nozzle, it's decreasing. For diffuser, it's increasing. Okay, now let's talk about what's going to happen what is the main objective of nozzle? The main objective of nozzle is to increase the velocity. So whatever the fluid you're passing through it, if you want to increase the velocity of the fluid, then we make it pass through the nozzle. Okay, now when we increase the velocity means the kinetic energy is being increased. But when the kinetic energy is increasing, that means where is this additional kinetic energy coming from? So it's not being created here. Rather, what happened is that we are converting one form of energy into other. So which energy is being converted into kinetic energy? It's the pressure energy. So basically what happened is that in case of the nozzle, at the inlet we have high pressure energy, but then as it moves from inlet to outlet, some of the pressure energy will be converted into kinetic energy, so the velocity of the fluid will increase and thus the pressure will decrease. Is this point clear for the case of nozzle?
Yes, sir.
Okay, now let's talk about the diffuser. Diffuser is exactly opposite to the nozzle. So in case of the nozzle, while we know that the velocity increase, when you see it for the case of diffuser, the velocity actually decreases. And for the case of diffuser, for the case of nozzle, the pressure decreases, but for the case of diffuser, the pressure actually increases. So in the diffuser, the opposite thing happens. We have an inlet. At inlet, we have a fluid with a very high velocity, and what we do is that we convert some of that kinetic energy to pressure energy. So the pressure is going to increase, the velocity is going to decrease, and this is what happens inside the diffuser. The diffuser and nozzle are basically just pipes, but nozzle is a pipe with decreasing diameter, diffuser is a pipe with increasing diameter. Nozzle increases the velocity, decreases the pressure. The diffuser decreases the velocity, increases the pressure. Okay, so these are the objectives, and this is the schematic diagram. The figure is a schematic diagram of the nozzle and the diffuser. Now let's analyze these devices based upon first law of thermodynamics. So the very first term in the first law of thermodynamics is Q. So Q is basically what? It's the amount of heat going into or out of the device. So in this case, Q, I have written here tick and cut. Both are possible. Okay, if it is said, you need to read the question carefully. If it is said in the question that the nozzle is adiabatic, if you read in the question that, let's say, the diffuser is well insulated, that means there will be no heat transfer to or from the nozzle and diffuser. But if it is not mentioned, and if it is mentioned that there is some amount of heat transfer, then obviously Q will be there. So Q, whether being there or not there, it depends. Both possibilities are there. You need to read the question carefully to know that whether the Q is there or not there in the question. Is this point clear or not about Q?
Yes, it's clear.
Okay, now let's talk about the next term. The next term is basically the work. Okay, for the case of nozzle and diffuser, they both are pipes. And since they are pipes, so we consider them having fixed boundary. So since they have fixed boundaries, and so we have no work going in or out of them. Okay, so work from them is neglected. Is not neglected. It's zero. There is no work done on them, or there is no work done by them. Okay, so W will be zero for them. Okay, now let's talk about change in the enthalpies. Okay, when we are saying that the pressure is going to reduce or pressure is going to increase, so what is enthalpy? Enthalpy is basically a combination of internal energy plus PV. So enthalpy is U plus PV. This is enthalpy. Okay, so when we are saying that the pressure is going to decrease or pressure is going to increase, definitely enthalpy is going to change. So this term will be there. These terms will be there for the case of nozzle and diffuser. The next thing is about the velocity. We are definitely saying in the objective that the velocity for the case of nozzle increases, for the case of diffuser decreases. So there will be change in velocity from inlet to our exit. So since there will be change in the velocities, so change in the kinetic energy term will also be there. Okay. Then the last term is about the change in the potential energy. Now the thing is that most of the time these nozzles and diffusers are applied horizontally. When you apply these nozzles and diffusers horizontally, when you place them horizontally, so essentially between the inlet and outlet, elevation difference becomes zero. However, even if you place them vertically, they are very small devices. Very small devices means that the actual elevation difference between inlet and outlet for these devices will not be too much. So the difference in the potential because of the fluid going in and out will be almost neglected. So if you look here, uh, this term potential effects from inlet to outlet could be directly neglected. So it could be just crossed out. So this is how when we apply the first law of thermodynamics over nozzle and diffuser. Is there anything which is not clear to anybody? Please feel free to ask.
No, sir, it's clear.
Okay. We are also going to apply these equations in numericals, and this is going to make things much more clear to you. But right now, let's have a look at these things on the summary sheet. Okay. Then the application, we are going to look at it later on. Okay, so two devices are done, the nozzle and diffuser. They are steady flow devices, so continuously flow can go in and out of these devices. So there is a continuous flow fluid moving in and out of these devices. Okay, so let's discuss another device, and this is known as turbine. Okay, so first of all, what is a turbine? Turbine is not just a simple device. It's basically a machine. Turbine is a big device. It's a heavy duty device. It's basically a machine. Okay. So what's the main objective of the turbine? The main objective of the turbine is to get work output. Okay. So normally what we have is that it's a big machine, and we make a fluid to enter into this machine, and the pressure is very high when the fluid is entering the machine. But then what it does is that it converts part of the pressure to work output. And this work output is very valuable because it is in the form of a rotating shaft. And if we connect this shaft to a generator, we can actually generate electricity. So we are going to get electrical output. So this turbine is a device to get the work output. Work output could be in any form. Okay, either it could be in the form of running an engine, or it could be running a generator and producing electricity. But there will be work output. So the main objective of the turbine is to produce work output. But how does this work output being produced? It converts the pressure energy to work output. So the pressure decreases. Okay. Schematically, how do we draw the turbine? We draw the turbine very similar to nozzle, very similar to diffuser. You see here, diffuser is drawn like increasing diameter, and this is how we draw the turbine as well, as increasing diameter. Okay. However, in case of the diffuser, the fluid goes in and out in the longitudinal direction, but here it's not like this. The fluid goes in perpendicularly, and fluid goes out as well as perpendicularly. And in the center, what we show is that there is a shaft going through the turbine in the center, and this shaft is something from where we get the work output. Okay, so this is the schematic representation of the turbine. Okay, and this is how the turbine works. It decreases the pressure, and while it decreases the pressure, some of the pressure energy is being converted into work output. Okay, and this is a big machine in reality. Okay. So do you understand what is a turbine? And do you understand what it does? Do you understand how we represent it schematically?
Yes, sir. There is a turbine moving inside of it, right?
Actually, we represent the turbine like this.
Yeah,
This is a turbine. Okay, there are moving components inside. You have blades. There are multiple blades of fans and things like that. It's a complicated device. It's a big machine. But obviously, when we are drawing it on paper, we just draw it schematically, and this is the schematic drawing of the turbine.
Yes. Okay, it makes sense.
Okay. Now let's move. Let's apply the first law of thermodynamics over them. Okay. So if we apply the first law of thermodynamics over the turbine, so have a look at it. First term is Q. Q, again, it could be there, could not be there, depends. If it is said in the question that the turbine is working adiabatically, or if it is said that the turbine is well insulated, obviously in this case Q will not be there. But if it is said that there is some heat transfer to or from the turbine, then Q will be there. So you have to read the question to know whether the Q is there or not. It could be there, it could not be there. Both possibilities are there. Is it clear?
Yes.
Okay, the next step is W. W will definitely be there because this is one of the objective of turbine, to have the work output. If no work output, then what's the use of the turbine? So W will definitely be there. So you will have W. Okay, and this is basically W out. Okay, now let's talk about the enthalpy difference. Since we say that the pressure is reduced, since the pressure is being reduced by the turbine, so definitely there will be enthalpy difference. Okay, because the pressure is one part of the enthalpy, so it will always be there. So when you are decreasing the enthalpy pressure, when you're decreasing the pressure, enthalpy will also be changed. So this term will be there.
So, sir, the enthalpy will always decrease?
Enthalpy most of the time, but yeah, actually it will decrease. Most of the time the enthalpy will decrease. Okay, so okay, then we'll have this term. This term is the change in the kinetic energy. Now, change in the kinetic energy depends upon change in the velocity. Now, velocity change depends upon what is the diameter of the pipe through which the fluid is entering into the turbine and what is the diameter of the pipe with which the fluid is leaving the turbine. Now, suppose if the diameter entering the turbine D1 is the same as the diameter of the pipe leaving the turbine, D2. If this is the case, then this term will not be there. Why? Because when the diameters of the pipe are same with which the fluid is entering the turbine and with which the fluid is leaving the turbine, okay, when the diameters of the pipe are same at inlet and exit, then basically the velocities will also be same. Okay, and so this term.
But you said that the pressure decreases. So if the pressure decreases, doesn't that mean that the velocity would increase?
No, if it was a pipe, then it is. What we are doing is that we are decreasing the pressure, but we are not converting the pressure energy into kinetic energy. We are not doing this. We are converting the pressure energy into work output.
Okay.
Okay. So this is the difference between nozzle and turbine. In nozzle, pressure energy is being converted into kinetic energy. Here, the pressure energy is not converted into kinetic energy. Rather, it is converted into work output. Okay. So the change in the velocities would depend upon the pipe diameters of inlet and exit. If the pipe diameters are different at the inlet and exit, then there will be change in velocity. If they are same, then there will be no change in velocity. So suppose if D1 at inlet is different than D2, then it will be there. Then the velocity change will be there, and then the kinetic change will also be there. Is it clear?
Say it. Yes.
Okay. The next thing is about the potential effects. Now, look here. Turbine, as I told you, is a big machine. Turbine is a big machine, but the problem is that most of the time we place the turbine in a horizontal position. When you place the turbine in the horizontal position, the inlet and exit for the turbine, there is not much elevation difference between inlet and exit. Okay, so the potential effect will be there when there is elevation difference, means Z1 minus Z2. But if the elevation difference is not too much, then the potential effects will not be there. So most of the time we place the turbine horizontally. Okay, since it's a big machine, there is a rotating shaft, so we are bound to place it horizontally. And when you place it horizontally, so from inlet to exit, the elevation difference is really not that much significant. So most of the time we can just cancel this potential change in the potential effect term. Is it clear?
Yes, sir.
Okay. So this was about the turbine. Okay, like for example, as I have told you, if for the case of nozzle, there is an opposite of it. No, the opposite of nozzle is diffuser. Similarly, for the case of turbine, there is also an opposite of turbine. And the opposite of turbine are and the opposite of turbines is compressor and pump. These two devices are opposite of turbine. Now have a look at it. Turbine produces work output. Compressor and pump need work input. You see, exactly opposite. Turbine reduces the pressure. Compressor and pump increases the pressure. Exactly opposite. You see, the turbine is the compressor and pump are exactly opposite to turbine in terms of their objective. Okay. However, what is the difference between compressor or pump? Suppose if you want to increase the pressure of a gas, then you're not going to use the pump, you're going to use the compressor. Compressor is used to pressurize the gas. Okay. However, suppose if you want to increase the pressure of liquid, then you're not going to use the compressor, you're going to use the pump. Okay, so the state of the fluid is different for the case of compressor and pump. However, the objective is same. Both objective is to produce high pressure, to increase the pressure. But when we are dealing with gases, we use compressor. When we are dealing with liquids, we use pump. If you put a gas through a compressor, you're going to damage the compressor. Sorry, if you're going to put a gas through the pump, you're going to damage the pump, because pump only deals with liquid. If you're going to put liquid into the compressor, you're going to damage the compressor, because compressors are only designed to deal with the gases. Since there's a huge density difference between gas and the liquid, so the device used to increase the pressure for both the cases are entirely different. So we use this compressor to pressurize the gas, and we use the pump to pressurize the liquid. Okay, so compressor and pump are exactly opposite to turbine. Okay, so turbine decreases the pressure and as a result produce work output. Here we need to supply work input. Normally, how do we supply work input? For the case of pump and compressor, they are not going to work until you connect them to electricity. So we supply electricity. So the electricity supply is basically the work input for the case of compressor or for the case of pump. Okay, so the electrical supply is basically the work input. Okay, and then we use this electrical supply to run these pumps and the compressors, and the pumps are going to increase the pressure of the liquid, and the compressor is going to increase the pressure of the vapor. Do you understand what is the relationship between pump, compressor, and turbine?
Yes, sir. I get it.
Okay, now schematically, if you look at it, turbine and compressor is represented exactly opposite to turbine. When you draw the turbine like a diffuser, but when you draw the compressor, we draw the compressor like a nozzle. Okay, so this is the schematic drawing of the case of compressor. But for the case of compressor, we show a shaft going in and out of the compressor, and this shaft shows work input. Okay, so there is work input into the compressor. And for the case of nozzle, it was in the longitudinal direction, the fluid was entering and leaving, but here we represent the fluid entering and leaving the compressor in the perpendicular direction. Okay, so 1 is entering here and 2 is leaving from here. Okay, so this is how we represent schematically the compressor. For the case of a pump, because the pump is an entirely different device, we represent it like this. Okay, so we have circle, and then after the circle at above we have a small pipe. Okay, we have fluid entering into the circle, which is the pump, this is the inlet, and then fluid exiting the pipe is basically 2, which is, and then we show here that there is work input onto the pump. So this is the schematic representation of the pump, this is the schematic representation of compressor, and this is the schematic representation of turbine. Is this thing clear?
Yes.
Okay, now let's have a look at the first law of application of first law of thermodynamics for all these 3 devices. Like for the case of turbine, it could be Q could be there, could not be there. Similarly, for the case of compressor, Q could be there, Q could not be there. You need to read the question carefully to know. If it is said that the compressor is well insulated, if it is said that the compressor is working adiabatically, then the Q will not be there. But if there is heat transfer from the compressor, then the Q could be there. So both possibilities are there. You need to read the question carefully to know that which possibility is actually the correct one. For the case of pump, since pump is dealing with the liquids, so in case of the liquids, in reality, the change in the temperature is almost negligible. And since the change in the temperature is negligible from inlet to outlet, so the Q amount of heat transfer is almost zero. So most of the case, it's not the Q is not there for the case of pump. So it's a very common thing that Q is not there for the case of the pump. But for the case of the compressor, Q could be there, could not be there. Both possibilities are there. But for the case of the pump, it's not possible to have Q there. Okay, so most of the time it's not there. It's basically just, you can ignore this term. Is it clear?
Yes.
Okay. Now let's talk about the work. Obviously, work is something important. For the case of turbine, it's work out, which is there. For the case of compressor and pump, it will be work in. So, but the work term you cannot ignore in any of these devices. Then we have the enthalpy. Since we are talking that pressure is decreasing in turbine and increasing in pump and compressors, obviously enthalpy term will be there as well. You cannot ignore that. Okay, let's talk about the change in the kinetic energy. For the case of compressor, it's like the turbine. Okay, so if the diameter inlet is different than the diameter outlet, okay, then this term will be there. However, if diameter inlet is the same as the diameter outlet, okay, then this term will not be there. For the case of the pump, most of the time inlet and outlet diameters are same. Okay, so you can just ignore the kinetic energy effects for the case of the pump. Okay, so in case of pump, in case of compressor, sometimes we have different diameter pipe at the inlet and exit. But for the case of pump, most of the time inlet and exit have the same diameter pipe, so the kinetic energy effects are neglected. And obviously for the potential effects are also neglected. Why? Because most of these devices are placed horizontally, and from between inlet and outlet, the elevation difference is almost negligible, so we can just ignore the potential effects. So this is the application of first law of thermodynamics over turbine, compressor, and pump. And the difference between compressor and pump is that compressor is used for gases, cannot be used for liquids, and pump is used for liquid and cannot be used for gases. So that's about these devices. Anybody want to ask anything so far? Everything is clear or not?
So for the pump, you said that there's no net heat transfer. Is it because water is passing through and it's a good?
No, the thing is that when you pressurize water, the change in the temperature is almost negligible. But when you pressurize a gas, the gas becomes heated, significantly heated. Okay, but for the case of water, because the water is almost incompressible, so the change in temperature is almost negligible. Since the change in temperature from inlet to exit is negligible, so there is almost no heat transfer. Okay.
Okay.
Okay. Any other thing anybody want to ask? Okay, let's move over to our slides and let's try to see what problems we have there and how to solve them. So here we were talking about the nozzles and diffusers. You can see here, this is the nozzle. Okay, the same schematic diagram I have shown you. This is the diffuser. This is the application of first law of thermodynamics over the nozzles and diffusers, but I have shown you on the summary sheet. Okay, so it's the same thing. So let's see a problem here. We have air. So first of all, each and every word is important because it says that air is the working fluid. So just consider this as the working fluid, air. Air enters an insulated diffuser. Insulated. Insulated means what? It means Q will be equals to 0, right? So air enters an insulated diffuser. So we are talking about diffuser here. Okay, operating at a steady state with a pressure of 1 bar, okay, a temperature of 300 Kelvin and a velocity of 250 meter per second. So let's draw a diffuser. The diffuser is drawn like this. This is our diffuser. Okay. Okay, so here we have inlet, here we have exit. This is 1, let's say this is 2. Okay, this is an insulated diffuser. Air is entering into it at with a pressure of 1 bar. So pressure is given and temperature is given, temperature 300 Kelvin, and velocity is given, okay, at the inlet. At the exit, the pressure is 1.13 bar. So we know what is the pressure at the exit. And the velocity is 140 meter per second. So we know what is the velocity. Potential energy effects can be neglected. Using the ideal gas model, determine the ratio of the exit flow area to the inlet flow area. So first of all, we need to find out the ratio of exit flow area to inlet flow area. So exit means 2, flow area means A. So we are talking about ratio A2 by A1. Exit flow area to inlet flow area. This is something we need to determine. And the exit temperature. Exit temperature means T2. Okay. So this is what we need to determine. Before moving towards the solution of the problem, first of all, do you understand the problem statement?
Yes, sir, it makes sense. See.
Okay. So let's try to solve the problem. Okay. So here we have air is entering into insulated diffuser. This is insulated. So you see here, there's insulated lines shown here. This insulated diffuser, we have P2 given, we have V2 given, we have P1, T1, V1 given. Okay, potential effects can be neglected. It is a steady state flow. So first of all, it is a steady state flow. So we can say that mass flow rate is same. So whatever the mass flow rate going in is the same as the mass flow going out. So since the mass flow is same, so we can say that we can write the formula for mass flow rate. It's A1 V1 over specific volume 1 equals to A2 V2 over specific volume 2. Since we are dealing with the gas, and we can use the ideal gas model assumption, so specific volume, we know that for at state point 1, for ideal gas, it's P1 V1 equals to RT1. For state point 2, it will be P2 V2 equals to RT2. That means V1 equals to R1 T1 over P1 and V2 equals to R2 T2 over P2. Let's replace the values of V1 from here and V2 from here into the equation. Okay, when you do this, since at the inlet and exit, it's the same air, so R is the same, so R would be cancelled, and we are going to end up with this thing, that A2 over A1, which is needed, equals to P1 over P2 into V1 over V2 into T2 over T1. Here P1 is known, P2 is known, V1 is known, V2 is known, T1 is known, but T2 is something which is unknown. So if you know T2, we can find what is A2 over A1. Is the solution procedure clear so far or not?
Yes, it's clear.
Okay, now let's talk about how to determine T2. So if you remember, we have, let's go to the diffuser equation. Okay, so if you go into the diffuser equation, so this is the diffuser equation. Okay, so in this equation, since it is insulated diffuser, so this term is not there. So let's ignore this term. This term is not there. Q. W is obviously not there. So we are just left with these two terms. Okay, so m dot h1 minus h2 plus m dot v1 squared minus v2 squared by 2. Okay, so let's have a look at it. Let's apply it. So you see here, this is our main fundamental equation. And then this term is 0 because it's steady state. This is Q is 0 because well insulated. W is 0 because, sorry, a different problem. Yeah, This is 0 because steady state. This is 0 because well insulated. W is 0 because no work is done by the diffuser. Then we have neglecting potential energy effects. We are end up with these two terms only. So this plus this equals to 0. Or we can say that H2 equals to H1 plus V1 square minus V2 square by 2. We know what is V1. We know what is V2. Okay. We can determine H1. How can we determine H1? Because this is air. Okay, so we can go into the table, and against the temperature, we can find out what is the enthalpy of air. So let's do this. If we go into thermodynamic tables, so table A17 is basically for the ideal gas properties of air. Table A17. Let's go to table A17. Okay, so we are dealing with temperature of 300 Kelvin. So if you look at temperature 300 Kelvin, so at 300 Kelvin, the enthalpy will be 300.19 for the case of air. Okay, so let's have a look here. So we know what is the enthalpy as well here. Just substitute the value, and we know what are the velocities. So we can find what is the final enthalpy. Okay. Now, once you have the final enthalpy, you can go back into the table, and corresponding to that enthalpy, you can find what is the temperature. So it's 321.64. So let's come here. 321.64 should be in between these two. So it's 320.29 and 325.31. So here we have 320.29 at 320 degree and 325.31 at 325 degree. So we can find out that at 321.64 enthalpy, what will be the temperature. And then once we have this temperature, we substitute this temperature into the formula to get what is A2 by A1. And this is how this problem is solved. Is there anything within the solution of this problem which is not clear? Please ask.
It's all clear.
It's all clear, sir.
Good, good. Okay.
Sir, I have a question regarding
Regarding?
nozzles.
Yeah, sure, please ask.
Sir, I wanted to ask that the working of a nozzle seems so counterintuitive because the area is decreasing. So shouldn't the pressure increase? Because if we think about it, the pressure should be more.
Okay. Your question is very nice. Because sometimes what happens is that in our layman terms, we speak something wrong, and then we develop an idea. So suppose if I have a pipe, let's say I'm in a kitchen, I'm in a washroom, and there is a pipe, and the water is coming out. We say, oh, water is coming very fast, it's coming with very high pressure, right?
Yes,
so we have an idea that when the water is moving at a very high velocity, definitely the pressure is high. Am I right? This is your question.
Yes, you're right.
Okay, it's because of actually we are also not wrong there. Okay, but let me tell you how it is. Look, the pressure, water is coming out, outside pressure is atmospheric, so definitely the pressure of the water at that time when it is coming out of the nozzle, it's atmospheric pressure that cannot change. The only thing is that when we say that the pressure is very high, it's because of the back pressure, the inlet of the nozzle. Okay, when the back pressure is high, then much of that pressure will convert into kinetic energy, and so the velocity of the fluid will be high. So at the exit of the nozzle, from where the water is coming out, at that point the pressure is not high, but actually the pressure is high at the back end where it is entering the nozzle. So normally in the layman term, when we say, oh, the water is coming with a very high pressure, okay, so it means, what we mean to say is that water is coming from a very high back pressure. That's why that back pressure is being converted, pressure energy is being converted into kinetic energy, and now the velocity of the water is very high at the exit.
Say that.
That makes sense?
Yes, I get it now.
Okay, okay. So any other thing anybody want to ask? It was a very good question. It was very good question. Okay. Okay, let's move ahead. Okay, so let's talk about the turbines. I already showed you the schematic of the turbine. It's like this. And we represented with the shaft. The shaft is connected to this, and we have perpendicular inlet to the turbine, perpendicular exit from the turbine. We talked about what's the main purpose of the turbine. It produces work, so there's work output. Okay, then how do we apply the first law of thermodynamics over it? All this information I just discussed with you in the summary sheet. Okay, and that is something is going to help you a lot. Okay, let's have a problem associated with it. Each and every word is important. So let's see, the problem starts. A well-insulated turbine. So first of all, you know it's a turbine. Then you know it is well-insulated, means Q is equals to 0. So a well-insulated turbine operating at a steady state develops 23 megawatt of power. 23 megawatt of power means this is W out. Okay, this is the output. Okay. For a steam flow rate of 40 kg per second, so we have, this is the mass flow rate, m dot. The steam enters at 350 degrees centigrade. So this is the inlet. So inlet is basically what? At 350 degrees centigrade, so that will be T1. With a velocity of 35 meter per second, so that will be V1, you can say, and exits as saturated vapor. Saturated vapor means we know what is, since it is talking about exits, so it should be X2. We know X2. When it is saturated vapor, X2 will be basically what? It should be 1, right? At 0.06 bar, so this is P2, with a velocity of 120 meter per second, so that will be V2. Neglecting potential energy effects, determine the inlet pressure in bar. So we need to determine what is the inlet pressure. Okay, first of all, do you understand the problem statement here? We have a turbine, well insulated, steam is flowing through it at 40 meter per second, 40 kg per second. The output of the turbine is given. The steam inlet conditions are given. What is, but inlet condition, only one inlet condition is given. That what is the temperature? The pressure is something we need to find. With a velocity of 35 meter per second, this is the inlet given. And at exit, we know that it is saturated vapor. We know what is the pressure, and we know what is the velocity. We need to determine what will be the inlet pressure in bar. Do you understand the problem statement here or not?
Yes, sir.
Okay. Now let's see the formula for the case of turbine. Okay, so let's talk about turbine here. This is turbine. So for the case of turbine, it's insulated turbine, so Q will not be there. We'll have W, and we will have this enthalpy change. And here the velocities are given, not diameter, but directly the velocities were given. If you remember here, look at the velocity. Inlet velocity is 35 meter per second, so velocity is given here, and the exit velocity is 120 meter per second. So the velocity difference is there. That means the diameter difference will also be there. But anyways, diameter is not given directly. The velocity is given, so it's okay. But that means this term will be there. So if we analyze here for the case of turbine, so we'll have these three terms in it. Okay, We'll have work, we have enthalpy difference, we'll have kinetic energy difference. Is it clear?
Yes.
Okay, so let's see the solution. Okay, so we have a situation like this. This is a schematic diagram. Okay, so there's work output, this is the temperature input, there's a velocity input, pressure output. We know it is saturated vapor, so that means X2 is 1, and we know what is V2. Okay, so all this information provided. Let's apply the first law of thermodynamics. So when we apply the first law of thermodynamics, because it is a steady state, this term will be 0. Well insulated, Q will be 0. This cannot be 0. Mass flow rate is provided. Obviously, the enthalpy term will be there. The velocity difference terms will be there, but the pressure, potential energy effect term will be neglected. So we're going to have situation like this. We know what W, we know what is m dot, we know what is V1, we know what is V2. Okay, let's talk about H1 and H2. So if you look here for state point 2, we know what is X2, we know what is P2. Since we know X2 and we know what is P2, so we can use these two things to find what is H2. Okay, so since it is saturated vapor at 0.06, saturated vapor at 0.06 bar, so that will be 6 kilopascal. Let's say if we go into the table, properties of steam, saturated water temperature table. No, I want saturated water pressure table. So this will be the pressure table. 6 kilopascal. 6 kilopascal is not there. Wow. That means we need to interpolate. So anyways, we can interpolate and we can find what is the enthalpy, which enthalpy we are going to take, because it is saturated vapor. So we're going to get the enthalpy of Hg. Okay, so we're going to get the enthalpy Hg. So we're going to interpolate and we're going to get the enthalpy Hg here. So if you do this, then this will be the enthalpy Hg. So this will be H2, right? This will be H2. So if you have H2, you can determine H1 because all of the terms are known in this equation. So you substitute everything into the main equation, you're going to get H1. And then what was our objective? Our objective was to find out the inlet pressure, Now, if you know H2, you can determine H1. And then if you know H1, then use H1 and the temperature to determine P1. Okay, so if you look here, so H1 comes out to be 3147.6. Okay, and now we know what is the temperature. Temperature is 350 degrees centigrade. So let's see at 350 degrees centigrade. Okay, 350 degrees centigrade. This is temperature. Okay, so 350 degree. This is 350 degree. At 350 degree, let us see the H values. So HF is 1671, Hg is 2563. And in our case, H value is how much? In our case, H value is 3147. So obviously this 3147 is bigger than Hg. So we will be in the superheated state. So we're going to leave this table. We're going to go into table A6. And then corresponding to, again, you might need to interpolate. So corresponding to that, you can determine what will be the pressure at that enthalpy. And the pressure comes out to be like about 15.2 bar. Okay. Since in this question, if you look here, it was asked to determine the inlet pressure in bar. So although we calculated first the inlet pressure in megapascal, but in the end, we needed to convert it into bar because it was asked in the question to convert it into bar in the end. So anyways, this is the solution for this problem. Is there anything which is not clear? Please ask.
So could you do the last part where we determine superheated state? Could you do that using the table?
Okay. So till here it is clear or not?
Yes, it's clear.
Okay. So let's go to the superheated state table. Okay. Superheated table. Okay. So now we have the enthalpy and what do we have? We have temperature. Temperature 350 degree. temperature 350 degree, and enthalpy is 3147. So let's see 350 degree and 3147. Okay, so this is 350 degree, and where the enthalpy is second last column. Okay, so you see here 350 degree, 3168. Okay, here we have 350 degree, 3166, 350 degree, 3162. Okay, 350 degree, 3158, 350 degree, 3154, 350 degree, 3150, 350 degree, 3146, and our was what? 3147. Am I right? 3147. Yes, our was 3147. So here at 350 degree, 3146 for 1.6 megapascal, and then 350 degree, 3150 for 1.4 megapascal. So at 1.4 megapascal, 3150, at 1.6 megapascal, 3146, and our value is 3147, obviously in between these two. Are you getting it or not?
Okay. Yes.
Okay. Okay. So we have this value here, and we have this value here. These two values.
Okay.
Our value is in between these two. So we come here, we write here at 1.4, it is this. At 1.6, it is this, and we want this, so we can determine that what would be the pressure interpolation. Okay, so this is how it is. Okay, next is the compressor and pump. We're going to do it in a minute. Okay. Okay, now because next week, next week is the midterm week, and you will not have lecture. So it's very important that you need to know that what is my way of checking the exam. Okay, now have a look at it. Suppose if this question comes in the, obviously this question will not come in the midterm exam because this is the chapter number 5, and you will have midterm exam till chapter number 4. Okay, but I'm just giving you an example. Suppose if this question comes in the exam, okay, and what happened is that a student is solving the question, and during the solution of the question, somehow the student made a mistake in this step. Okay, so he found the pressure wrong. Okay, so what will happen? When your pressure goes wrong here, then you're going to substitute the value here, and so your next enthalpy going to go wrong here. And then once this enthalpy is going to go wrong here, then corresponding to that, your final pressure is also going to wrong. So it's just because you did a mistake at this step, all gone wrong, right? So a student might think that, okay, since all my values are wrong, so maybe I'm going to get 0 marks, okay? But in reality, my way of grading is not like this. Suppose if I give this question, so I would dedicate marks for all the steps. For example, drawing the diagram, 2 marks. Let's say it is 10 marks question, okay? Then writing the main formula and putting, substituting values, canceling out the terms, okay, 2 marks. Then this is step 2 marks, this is step 2 marks, and the last step 2 marks. So it will be 10 marks, right? So you made a mistake in this step. Okay, so let's say I'm going to deduct 1 mark for your mistake in this step. Okay, so for all other steps, although your answers are wrong, but I will realize that your answers are wrong because you made a mistake in this step. So all other steps, your procedure is correct, but your answers are becoming wrong because of only this step. Okay, so you will still get 2 marks here, your grade still get 2 marks here, still gets 2 marks here, and 2 marks here. So in this question, you're going to get 9 out of 10 in this case, right? So don't be worried, because when you're going to be solving the problems, you're going to take the numbers from the table, you're going to write it into your answer sheet, and there is a huge chance that you take a wrong value. The human error factor will be there. Okay, maybe you're calculating and you do some wrong calculation. Okay, so the numbers are not important here for me. The procedure is important. Yes, if you do mess up in numbers, you're going to have some reduction in mark, but only for that specific step. Even if your numbers are going wrong later on, just because of that mistake which you did in the earlier step, your marks are not going to be detected for the other steps. So your marks will be detected only for the specific step where you're going to make the mistake. And then the procedure is very important. And this means the way you write your solution, the steps are important, because if you have written the steps, even you made a mistake, you will still going to get the marks for the steps. So is this thing clear?
Okay, sir. Thank you, sir.
Okay, so sometimes it happens, right now not, but when you come to chapter number 9 and 10, you will have problems like 3-4 pages long problems. And sometimes it happens that the student do mistake in the very first step, and then later on, whole solution is correct, procedure is correct, but all numbers are wrong because everything dependent over one another. So, but still the student, my way of checking is that I do not detect all the marks. I just detect the mark for the specific step where you make the mistake. Okay, and for all other steps, because of the procedure, I'm going to give you the marks. Okay, so don't worry if you feel that, oh, because during the exam you won't have much time, so you might get a bit confused that, okay, maybe I'm going to do some mistake and it's going to ruin my question. No, if you do the mistake, only that specific step will be deducted, but not the whole question. Okay, anybody want to ask any other thing? Okay, so let's, yes, somebody was asking something. Somebody was asking something. Okay, let's have a break of 5 minutes, and then we're going to be back, and we're going to start from where we stopped. Is it okay?
Okay, sir.
Please put your attendance on this. Please put your attendance on the chat box so that I'm going to mark you present. Okay. So just write your ID and mark present. Okay. Okay. Assalamu alaikum. Can you hear me?
Walaikum salam, sir. Ji, sir.
Okay. Now let's apply the first law of thermodynamics over compressors and pumps. Again, regarding the schematic diagram and their working operation, I've already explained it to you in the summary sheet, and what terms will be cancelled, that has also been discussed before. Okay, so let's come over to the example. So we have here air. So we're talking about air at 100 kilopascal and 280 Kelvin. 100 kilopascal means, so this will be the initial pressure, and 280 Kelvin means initial temperature, is compressed steadily to 600 kilopascal. So this will be my final pressure, and 400 Kelvin, this will be my final temperature. The mass flow rate of the air is 0.02 kg per second, so that's the mass flow rate, m dot. And a heat loss of 16 kilojoule per kg occurs. Now have a look here. There is a heat loss of 16 kilojoule per kg, means that the compressor is not adiabatic. So this is Q. This is Q, but I will not write here capital Q. I will write here small q, because it's not in kilojoule, it's kilojoule per kg. It's kilojoule per kg, so I'm going to write here small q. This is small q, but if you know small q, you can find capital Q, because capital Q is basically m dot mass flow rate. If you multiply with q, it's going to give us in kilowatt. Okay, So this is the amount of heat loss. So that's Q. Okay, this occurs during the process, assuming the changes in kinetic and potential energies are negligible. So here, both kinetic and potential energies are negligible. So that means velocity inlet and velocity exit are same, and also the elevation inlet and elevation exit are same. Okay, so that's why we can ignore the kinetic and potential energy changes. Determine the necessary power input of the compressor. So we need to find what is work in for the case of compressor. Okay. Do you understand the problem statement right now or not?
Yes, sir.
So let's have a look at the solution. So first of all, let's have a look at the formula for the case of the compressor. This is the compressor. Okay, so in this case, Q is there, so this term is there, and W will definitely be there, and change in enthalpy will also be there. Okay, but kinetic and potential energy effects are not there. So these three terms are here in this. These three terms. Okay, so Q is there, W is there, and m dot h1 minus h2 will be there, obviously. So let's apply it. So let me write here first. So it will be Q minus W plus m dot h1 minus h2. This is what we have here. Okay. In this question, we need to find W. Okay, but Q is provided, and Q is basically heat loss. Okay, remember, Q is basically Q in minus Q out. Okay, and Q in is not there in it. Okay, so this term is 0, but Q out is given, heat loss is given. So Q will be negative in this sense. Okay, so let's apply it. In the case of compressors, okay, so we'll have like this. So we'll have W in, whatever the W we have here, it will be W in will be equals to m dot Q out. Why? Because Q was given as per unit mass, so we have to multiply with the mass flow rate plus m dot h2 minus h1. So now we know what is Q out, okay, and we know what is Q out, we know what is m dot. So if we know what is h1 and h2, we can determine what is W in. We can determine h1 and h2. Why? Because we know what is P1, T1, we know what is P2, T2. Okay, so we can just directly go into the table. Table A17 is basically for the case of air. Now these things should be on your fingertips. That if it is air, which table you have to go to? Table A17. So go to table A17. Okay, corresponding to table A17. Now, what are the temperatures? 280 Kelvin and 400 Kelvin. So let's have a look at it. So this is 280 Kelvin. So at 280 Kelvin, the enthalpy is this. At 400 Kelvin is the last one here shown, and enthalpy is here. So 400.98 and 280.13. So 280.13, 400.98. Just substitute the values here into the main equation. You're going to get what is the work input. Is this thing clear or not? Anything, any step which is not clear in it, please ask.
It's clear here.
Okay, the next thing are the heat exchangers. Now let's discuss about the heat exchanger. First, let us try to discuss that what heat exchanger is. What is a heat exchanger? So heat exchanger is basically a device to exchange heat. Now, suppose I have one fluid which is hot, another fluid which is cold, and now I want heat to be transferred from the hot fluid to the cold fluid. Now what I don't want the two fluids to mix together. But what I want is that just the heat be transferred from the hot fluid to the cold fluid. So what I'm going to do is that I'm going to take a pipe. On inside of the pipe, I'm going to make one fluid to flow, and over the outside of that pipe, I'm going to make the other fluid to flow. So the two fluids will be in contact with each other, not directly, but through the pipe. Okay, so they are going to transfer heat from hot to the cold fluid through the pipe. In this way, heat will be transferred, but the two fluids are not going to mix with each other. So you can see the example here that this is our heat exchanger. Okay, so let's say one fluid is going through the inner pipe, okay, and the other fluid is passing through the outer pipe, where it obviously goes from the top of the inner pipe, okay, from the outside of the inner pipe, and so both the fluids are in contact with the inner pipe. Okay, so one at the outside of the inner pipe, one in the inside of the inner pipe. Okay, and so through the pipe they are going to transfer heat to each other. Okay, so this is the heat exchanger. Okay, so now when we have to analyze the heat exchanger, okay, then one important thing is that we need to set our control volume. Okay, what is our system? If we consider the whole heat exchanger as our system, both fluids inside it, then what happens is that we say that this is our system and outside is our surrounding. Then in this case, from outside to inside, there is no heat transfer. Okay, so Q will be 0 in this case. Okay, so Q will be 0 if we are considering our if we are considering our whole heat exchanger as our control volume. However, suppose if we are considering only one of the fluid as our control volume, then if it is one of the fluid as a control volume, then Q will not be 0, because this is what is needed. We need to transfer heat from one fluid to the other fluid. If we are considering only one fluid as our system, then the Q will not be 0. But if we are considering the whole heat exchanger as our system, then whatever the heat exchange is taking place is between the two fluids and it's inside the system. So from between the system and the surrounding, then Q is 0. Do you understand this point or not?
Yes, sir. ठीक है.
Okay. Now, for the case of heat exchangers, let's try to analyze what are the different terminologies we have in here for the case of heat exchangers. So look here. First of all, the heat exchangers, in short form, we write it as HX. HX is heat exchanger. The main objective is to transfer heat. Okay, how it is done? We have a pipe. Inside the pipe, we have one fluid, and outside the pipe, we have another fluid. And the two fluids are in contact with each other through the pipe, not directly. Okay, so now it depends upon what is our control volume. If our control volume is the complete heat exchanger, then Q will not be there. But if our control volume is only one fluid, then Q will be there. Okay, so this is about Q. Is this thing clear?
So what are the arrows indicating?
Arrows indicating the direction of flow. It doesn't matter whatever is the direction of flow.
Okay.
It could be like this. It could be like this. Important thing is that one fluid is inside the pipe, one is outside the pipe. And both are in contact with the pipe so that they can transfer heat. This is important. Okay. Okay. And now let's talk about the work done. There is heat transfer between the two fluids through the pipe. There is no work done. Why? Because for work done, there has to be some boundary motion, the circular motion, rotatory motion, translation motion. But there is no motion here. For the case of, and our pipe is a fixed boundary, so work done is not there at all. Okay, we talk about enthalpy change. Enthalpy change will be there. Why? Because enthalpy is a factor of U plus PV. Now in this case, we are assuming that PV is not changing. In the case of heat exchanger, we presume that the pressure remains constant. So pressure is not changing, but what is changing is the temperature. Since the one fluid is gaining heat, one is rejecting heat, so there is going to be change in temperature. That means there is going to be change in internal energy. So H will change. So this term will be there, okay, in any case. Then talk about the change in the velocities. Most of the time in the heat exchangers, the pipe going into the heat exchanger and the pipe leaving the heat exchanger have the same diameter. If they have the same diameter, that means they have the same cross-section area. That means they have the same velocities. That means there is no change in velocity from inlet to exit. So this term will not be there. Also, the heat exchangers, comparatively, they are not really that much big, and so the potential energy effects can be neglected between the inlet and the outlet. Okay, so this is not there. This is also not there. Okay, this term is also not there. So what's left? Just the enthalpy term. And if we are considering one fluid, then Q. And if we are considering the complete heat exchanger, then this term is also not there. So what's basically here is that we have now, but here it's not necessary that we have just one fluid. Okay, so since we have at least two fluids at the same time, so let's have a look at here. For the case of heat exchanger, when we analyze, we have a situation like this. Let's suppose we have one fluid going through the pipe inside, okay, like this. We have other fluid flowing over the pipe and going out. So let's say water is flowing from here, R134A is flowing inside the pipe. Okay, so if I consider this as a whole heat exchanger, then I have two inlets, one inlet for this fluid, other inlet for this fluid. So these are the two inlets. And then at the same time, I also have two outlets, because one outlet for this fluid, other outlet for the other fluid. Okay, so in this case, what we do is that we do the mass balance and the energy balance. When we do the mass balance, what we say is that summation of all the mass inlet is equals to summation of all the mass outlet. Okay, mass flow rate outlet. So mass flow rate inlets will be what? Here in this case, M1 plus M3. Here in this case, outlet will be M4 plus M2. Okay, so it will be M1 plus M3 equals to M4 plus M2. And then we have another thing, which is the energy balance. When we do the energy balance, we already saw that there is no other term left. It's just the enthalpy term. So if you just consider the enthalpy term, so it will be all the enthalpies going in minus all the enthalpy going in minus all the enthalpy going out equals to 0, or you can say all the enthalpy going in equals to all the enthalpy going out. So it will be m.1 H1 plus m.3 H3 equals to m.2 H2 plus m.4 H4. So it was m.1 plus m.3, just add H's to all the terms, and this will be the energy balance. Okay, so these are the two equations which we are going to use in order to solve for the case of heat exchangers. Okay, now suppose if we are considering our control volume as only one fluid, then Q will be there. Okay, then Q will be there. Q will not be 0. In this case, it will be Q plus, now it will be only one mass flow rate because our system is only one fluid. So it will be m dot H1 minus H2 equals to 0. Okay, so in case we are considering only for one fluid, then this will be the formula. In case when we are considering for the complete heat exchanger, then it is summation of mass inlet equals to summation of mass outlet and summation of m dot I HI equals to summation of m dot O HO. Okay. So then we have these formulas. I've written the formulas here. Here, these are the two. So for the case of heat exchangers, it's like this. M dot inlet summation of this is equals to m dot outlet, and m dot IHI equals to m dot OHO. Is this thing clear so far or not?
So it's clear, but I have one question about heat transfer.
Yeah, we're going to do the question about heat transfer. Yes.
So I wanted to ask one thing. So in the complete heat exchanger part, shouldn't there be no change in enthalpy? Because
No,
the whole system has the same enthalpy, right?
no. What we are
Because
saying is
there's
that what we are saying is that the total energy is constant, but the enthalpy of individual fluid is changing. So what we are saying is that enthalpy of, let's say there are two fluids entering, so summation of enthalpies of these two fluids will be the same as the summation of enthalpies of the same fluid exiting. So summation MIHI is equals to summation MOHO. Summation is same, but
okay.
enthalpy is changing because the one fluid is gaining heat, other is losing heat. Is it clear?
Say okay.
Yeah.
Yes, it's clear.
Okay, so let's come over to a problem related to the same heat exchangers. We have R134A is to be cooled by water in a condenser. The refrigerant enters the condenser with a mass flow rate of 6 kg per minute. So we have this R134A cooled by water. Okay, so we have a situation like this, that 134A is entering from point 3 and leaving from point 4. So this is all inside the pipe all the time. Okay, and water is entering outside the pipe and then flowing over the pipe and then getting out from here. So at state point 1, water is entering, and at state point 2, water is leaving. Okay, so the refrigerant enters the condenser with a mass flow rate of 6 kg per minute. So we have what is the mass flow rate of the refrigerant. So mass flow rate of the refrigerant will be the same as the mass flow rate 3, which will be the same as mass flow rate 4. Okay. At 1 megapascal and 70 degrees centigrade. So we know what is the pressure and we know what is the temperature. And leaves at 35 degrees centigrade. And we know what is the temperature of leaving. The cooling water enters at 300 kilopascal and 15 degrees centigrade. So 300 kilopascal and 15 degrees centigrade. This is the temperature at which the cooling water enters. And leaves at 25 degrees centigrade. So it leaves at 25 degrees centigrade. Neglecting any pressure drop. This is a very important and significant. This is a significant sentence. Neglecting any pressure drop. What does it mean? When it says neglecting pressure drop, means whatever the pressure is at the inlet is the same as the pressure at the outlet. So the refrigerant is entering at 1 megapascal and is also leaving at 1 megapascal. Because neglecting pressure drop. Similarly, water is entering at 300 kilopascal and is also leaving at 300 kilopascal. Why? Because neglecting pressure drop. Okay, so neglecting any pressure drops, determine the mass flow rate of the cooling water. So we need to know that what is the mass flow rate of the cooling water. So m dot w. This should be the same as m dot 1. It should be the same as m dot 2. But we need to determine it. So determine the mass flow rate of the cooling water required and the heat transfer rate from the refrigerant to the water. So Q. This is what we need to determine. Okay. First of all, do you understand the problem statement or not? Is the
Yes,
problem is okay? Okay, so let's try to solve the problem. First of all, since we need to find out the mass flow rates, so it's better to consider the whole heat exchanger as our control volume, because then there's no Q. So it becomes really easy to solve, okay? So we have summation MIHI equals to summation MOut H out, okay? So we have, okay, let's talk about enthalpy, because we know the temperature and pressure of at all points. So here we know what is the temperature and pressure, so we can find enthalpy here. We know temperature, pressure, we can find enthalpy here. We also know temperature and pressure here, so we can find enthalpy here. And then we also know the temperature and pressure here. So we can find enthalpy here. So we can find enthalpy at all 4 points, because at all 4 points, we know what are the temperatures and pressures. Let's have a look at one of the point. Let's say 300 kilopascal, 15 degrees centigrade for water. So let's have a look at it. Let's go to water. (300 kilopascal). So where it is 300 kilopascal, this is 300 kilopascal. Okay, and at 300 kilopascal, saturation temperature is 133. Okay, so since saturation temperature is 133 and our temperature is 15 degree, so what do you think? Our temperature is less than saturation temperature. So which table? Compressed liquid, exactly. But we can use the approximation, just ignore the pressure. So we will ignore the pressure. We will go into the temperature table, 15 degree. We go at the temperature table at 15 degree and get the enthalpy HF. So this will be the HF. Okay, so it will be 62.982. It will be at this point, you can check. Yes, enthalpy H1, 62.982. Okay, similarly, you can find all other enthalpies. Okay, so it's the same procedure that you need to go into the table. First, go into the saturation table, figure it out that which table you should be in, and then go into that specific table and get the value of enthalpy. So this is for the case of water. This is also for the case of water, inlet and exit. This is for the case of R134A, and this is also for the case of R134A, inlet and outlet. So we have all the inlets, we have all the outlets. So we have H1, H2, H3, H4. So once we have this thing, we know what is the mass flow rate of the refrigerant. So that means we know what is m.3, we know what is m.4. And there is only one mass flow rate left, which is mass flow rate of the water. So we get this equation where we have all the things known. We have this thing, this equation, we get all the things known. H1, H2, H3, H4, mass flow rate of the refrigerant is known. We can determine what is the mass flow rate of the water. Okay, so these are the H's, and then we can find what is the mass flow rate of water. Do you understand how we determine the mass flow rate of water?
Sir. I get it.
Okay. Once we have the mass flow rate of the water, that was the first part of the question. In the second part of the question, it was asked to determine the Q. Now, when you have to determine the Q, now you cannot consider the complete heat exchanger. Now you have to consider only one of the fluid, because then the Q is there. Okay. So let's say if we consider water as our fluid, then our formula will be this, that Q is equals to m dot water H2 into H2 minus H1. We know what is H1, we know what is H2. Okay, so we know what is mass flow rate of the water. Just substitute all the values, you're going to get what is Q. Okay. So this is how we solve the problem. And with this, our problem of the heat exchange is over. Anybody want to ask anything? Okay, the way we solve for the case of heat exchanger, exactly the same way we are going to solve for the case of mixing chambers. Mixing chamber is basically what? So it's like in our homes, in our kitchens, washrooms, you see there is one cold water supply, there is a hot water pipe, and then there is a faucet. जो नल लगा हुआ होता है, you open the hot water, you open the cold water, and here the mixing occurs, and then you get the output at whatever the temperature you need. Okay, so this is a mixing chamber. So you will have two inlets. You will have two inlets, m.1 and m.2, and those two are going to mix and going to get m.3. Now, in this case, again, we're going to apply the same methodology as we apply for the case of heat exchanger. We can do the summation of all the enthalpies at the inlet equals to summation of all the enthalpies at the exit. So it will be m.1 plus m.2 equals to m.3, and in terms of the energy, it will be m.1 H1 plus m.2 H2 equals to m.3 H3. So the same way, we will consider Q0, we will consider W0, kinetic energy 0, potential energy 0. All these terms will be considered 0. This will be our main equation to solve the problem correspondingly. So I have not added the question of mixing chamber in this in the slides here, but you have 1 or 2 questions in the practice problem, and also you have an example problem there in the book. So I would like you, and I would request you to go through that problem for the mixing chamber. It can come in exam, obviously not in the midterm, but in the final. Okay, so just go through it. It's the same way solution as we did for the case of heat exchanger. In fact, the heat exchanger was a bit more complicated than the mixing chamber, because heat exchanger, one time we need to consider it as a complete heat exchanger, other time we need to consider it as for one fluid. So 2 separate kind of analysis was done in the same problem. But in the case of mixing chambers, we don't need to go through 2 separate kind of problems. So it's just one mixing chamber. We can consider just this equation, and that would be enough. So you can go through the problem solution yourself in the book, and it's simple, it's easy, and also there is some problem in the practice problems. So this is the mixing chamber. It's, if you see here, written here in the bottom, mixing. Okay, there is no any specific schematic diagram for it. Okay, but anyways, the same formulas you're going to use like you use for the case of the heat exchanger. Now there is only one last device left, and which is the throttling device. Now, what is this throttling device? Throttling device is like a device which significantly drops the pressure by restricting the flow. Okay, and the most common and easy example for it is basically if you go to a hair shop or salon, you're going to find they spray water on your hair. So this is spray bottle. The spraying mechanism is the throttling mechanism. What happens is there, you increase the pressure by you produce the pressure by your finger when you press the lever of the spray bottle. Okay, and then that pressure, it becomes your back pressure, and then it passes through the spray nozzle, and the spray nozzle is basically what it is, just a restriction. And when you have a significant back pressure and you have huge restriction for the flow, then small opening causes a significant disperse of water into the air. Then that dispersion of water is a specific phenomena. We call it throttling. Okay, and how does this throttling works? What happens inside of throttling? Since we are restricting the flow and making the flow to pass through a very small space, very small opening. Okay, so overall enthalpy remains same in this case. Okay, because for the enthalpy to change, we need some space. Okay, so if the space is very limited, then the enthalpy change is not going to be there. So enthalpy at the inlet will be the same as the enthalpy at the exit. This is the fundamental thing in case of the throttling device. But what happens is that significantly pressure is reduced. Okay, because outside pressure is the atmospheric pressure, and inside pressure you develop the pressure by the lever, by pulling the lever of the spray bottle. So the back pressure is significantly higher than the atmospheric pressure, and so there is a significant abrupt drop in the pressure. So enthalpy is basically what? It is internal energy plus PV. Okay, and when we are seeing that the enthalpy remains constant, so what happens is that the pressure is reduced significantly, but in order for this thing to remain constant, the specific volume increases significantly. Okay, so what happens is that there is a bit evaporation. Okay, or you can say that there is a change in the phase that occurs. So whenever the spraying is done of the water, you will find water vapors generated very quickly, and that produces the cooling effect. Okay, so suppose if I have a barber, if I go into the barber shop and saloon and they spray water on my head, I feel cold. Why? Because the water, there's a significant increase in the specific volume, and thus causes the phase change process. And in the case of phase change process, it takes the energy from the water itself, making the water cool. So anyways, this is the throttling device. I have also placed a video regarding the throttling device in the Google Classroom for this chapter, chapter number 5. So you can also watch the video where they have shown a specific throttling device. so that you can have an idea how does the throttling device works. So it's basically spray nozzle. Okay. So what happened in case of the throttling device? What happened in case of the throttling device? The pressure reduces significantly, and as a result, however, the enthalpy remains constant. Enthalpy remains constant. Because of the pressure reduction, there is a temperature reduction as well. However, enthalpy remains constant. Okay, and this is a fundamental thing in the analysis of throttling devices. Okay, let's talk about how do we represent the throttling device. So let's go to the last sheet. Okay. Okay, so when we talk about the throttling device, what's happening inside the throttling device? Pressure decreases significantly. So this is one thing, but the enthalpy remains constant. Enthalpy remains constant. How do we represent the throttling device? It's basically a valve. It's basically a valve. So we have an inlet to the valve, we have an exit to the valve, like this. Okay, for the case of throttling device, there is no amount of, there is no heat transfer from the system to the surrounding, there is no work done. The only thing is that the enthalpy is constant from inlet to exit. Okay, this is the main thing in order to analyze for the case of throttling device. So let's see a problem related to it, and things will become much more clear when we solve this issue. Okay, we have a refrigerant R134A. It enters the capillary tube. Capillary tube is basically a throttling device of a refrigerator as saturated liquid at 0.8 megapascal. Saturated liquid means we know what is X. So X1 is equals to 0 because it is saturated liquid. At 0.8 megapascal, that means we know the pressure. So P1 is given and is throttled to a pressure of 0.12 megapascal. So we know what is the pressure P2. Determine the quality of the refrigerant at the final state. So we need to determine what is X2. Okay. And the temperature drop during this process. Temperature drop means delta T, means T1 minus T2. This is what we need to determine. Okay. So first of all, do you understand the problem statement? Do you understand the problem statement? Okay. So let's try to solve the problem. Okay. So the logic will be what? Since we know the properties at the state point 1, we know X1 and P1. So we're going to use X1 and P1. Yes, okay. We're going to use X1 and P1 to determine what is H1. Okay. And also we can determine T1. Okay. Once we know H1, then since it is a throttling process, we say that H1 is equals to H2. So we know H2. Then using H2 and P2, we are going to determine X2 and T2. X2 is something which was needed, and then once we have T1 and T2, so we can use this here to get delta T. This will be the logic. Okay. So first, let's have a look at the solution. We have R134A as saturated liquid at 0.8 megapascal. So let's go to 0.8 megapascal and see the saturated liquid value. R134A. Okay, so what were the conditions? 0.8 megapascal. So here it is, pressure table. So 0.8 megapascal means 800 kilopascal. At 800 kilopascal, the temperature will be T1. This is 31.31. And then what we need is, what do we need? We need enthalpy. So enthalpy will be HF. So HF will be 95.47, right? So this will be our H1. So this will be our H1 and T1. Once we have H1, let's say this H1 is the same as H2, but now we need to find it out that what will be the X for this case, okay? So the pressure is 0.12 megapascal, means 120 kilopascal. So corresponding to 120 kilopascal and the same enthalpy, let's see. So 120 kilopascal, this is 120 kilopascal. So this is HF, this is Hg, and our H is this one. Obviously, our H 95.47 is in between 22.49 and 236.97. So we can use this to find what is X. So our formula will be H is equals to HF plus X HFG. Okay, so H is known. This is the H. Okay, this will be the HF, and this will be HFG. So you can substitute these values and you can find what is X. And correspondingly, this will be the temperature, and then you can see what is the difference between this temperature and this temperature, T1 and T2. So this was what was all needed. So this problem is solved. So anything which is not clear in the solution here, please ask.
It's clear, sir.
Okay, good. So anyways, if we look at the summary here, so we discussed the application of first law of thermodynamics to open systems under steady state conditions. So it's normally said SFSS. SFSS is basically steady flow, steady state systems. Okay, so since there are steady state systems, so change in the internal energy and kinetic energy, potential energy terms with respect to time will be zero. Okay, so the only specific terms that we are going to consider are the ones which are occurring across the boundary. So you'll have Q minus W plus E mass in minus E mass out equals to 0, where E mass in and E mass out, since the fluid coming in and going out of the boundary will have some kinetic energy, will have some potential energy, will have some enthalpy. So we are going to discuss what are the enthalpy differences, or the kinetic energy, or the potential energy differences for the fluid going in and out of the control volume. Okay, so we talk about different devices. We have nozzles, diffusers. They're like pipes. Nozzles is used to increase the velocity. Diffuser is opposite of nozzle. It decreases the velocity but increases the pressure, but they are simply pipes. Turbines, compressor and pumps, they are basically machines. Turbine is used to produce work output. Normally this work output is connected with generator to produce electricity. Compressor and pumps are opposite to turbine. They take electrical energy in the form of work input and produces high pressure. Okay, and then we have heat exchangers and the mixing chamber. For the heat exchanger and mixing chamber, we have similar kind of analysis, where we have summation of mass flows should be equals to inlet for inlet and outlet should be same, and then we have the energy balance, summation mi hi equals to summation m out h out. Then we have the throttling device. For the case of throttling device, these devices decreases the pressure significantly, but one important thing for throttling device is that enthalpy remains constant. Okay, so this is the fundamental thing about the throttling device, and we can apply it in our analysis. We did it to solve a problem related to it as well. So anyways, this was the summary of this chapter, and with this our chapter number 5 is finished. So anybody have anything to ask, you can ask. Otherwise, this chapter is finished. Are you catching up with me or not?
Yes, sir, it's all good.
Okay. The course itself is not really that difficult, but you need to really do some effort. You need to work a little, and then inshallah things will be okay. So anyways, with this our chapter number 5 is finished. We applied the first law of thermodynamics to the control to closed systems in chapter number 4, and then to the open systems in chapter number 5. And with this, our application of first law of thermodynamics is now complete. We are done with the first law of thermodynamics. Next week, you are going to have your midterm exam. And inshallah, after the midterm exam, next week, we are going to start with the second law of thermodynamics. So with this, I'm going to stop my lecture here. And if you have any question, please feel free to ask. Anything regarding the quiz, anything regarding the assignments, anything regarding the exam that you have next week, midterm exam, you can ask. Okay, if no other question, then I can finish my lecture now. So that's it.
Okay, sir. Everything's clear. Thank you.
Okay. Anyways, thank you, and Allah Hafiz.
Allah Hafiz, Allah Hafiz.
Okay, sir. Okay, thank you, sir. Allah Hafiz, sir.
Allah Hafiz.